So whole body exposure is sort of the worst case, and this is the thing that really tends to stick in people's imaginations and their memories. This is, for instance, what was seen in the emergency workers who were first on scene at Chernobyl. And of these people, there were 28 deaths from this type of exposure at that time. And this causes acute radiation syndrome. And again, this is whole body exposure from a significant high dose of radiation. What this consists of is a prodrome of initial symptoms such as nausea and vomiting, diarrhea, neuromuscular symptoms such as fever and headache, low blood pressure, things like that, sort of constitutional type symptoms. And the rapidity with which these come on, does it come on in a few minutes? Does it come on after a couple of hours? And how long it lasts and how severe it is are all related to the magnitude of the dose. And so the faster and the worse the symptoms are, the higher the dose has been, and the worse the outcome is likely to be for the exposed person. So in discussing acute radiation syndromes, it's divided into three major types. The highest dose, which is 50 gray, which is a tremendous dose, about 50,000 millisieverts, so compare that to 0.06 millisieverts for chest x-rays, causes something called the cerebrovascular syndrome. And basically the nervous system, the circulatory system, they shut down, and the person is very quickly affected and dies within 1 to 2 days. And this is an extremely severe type of sickness, and this only occurred in a very few people, even in the Chernobyl situation, because they were right there in the reactor room. The intermediate doses from 5 to 12 grays cause something called the gastrointestinal syndrome, because what it does is this radiation is enough to affect the rapidly dividing cells that keep the intestinal tract populated with the cells you need to fight off infection, contain fluids, absorb food. And what happens is these are normally replaced very rapidly by your body, but if you can't replace them anymore, then you end up having a syndrome where the person loses all kinds of fluid and electrolytes, and without medical support, someone affected by this would die within a few days. Fortunately, if someone is affected at this level, there are a number of things that can be done now in terms of fluid support, antibiotics, et cetera, to bring them through this period. At a lower dose, about 2.5 to 5 grays, you see something called a hematopoietic syndrome. It affects the bone marrow. And these people will have bone marrow suppression. They stop replacing the blood cells that are normally are used up during normal processes in the body. And these people tend to die without medical help after several weeks because they can no longer fight infections and they can no longer clot their blood. And so they have a lot of problems with that sort of thing. And again, this can also be helped with antibiotics, with marrow-stimulating agents, which are now available and are used, for instance, in patients with cancer undergoing chemotherapy. They'll give marrow-stimulating agents. They're also useful in this type of situation. Fortunately, this type of acute radiation syndrome affects very few people in a radiation emergency. So this might affect, as at Chernobyl, the people who were the plant workers who were right there, who were trying to, in the acute stage, trying to do something to shut things down, or the emergency responders who came in and were exposed to large amounts of radiation. But most people, even in the vicinity of a nuclear accident, do not have to worry about something this severe. We're concerned about other effects from external and internal contamination, which are much more subtle, do not cause such severe immediate illnesses, but may have longer-term concerns. So that's what I'll speak about next. Now, external contamination would be, for instance, someone who was downwind of a release of radiation, say after one of the steam explosions, for instance, at Fukushima. When the cloud goes over, it falls on you, and you can have radiation deposited on your skin, on your clothing, something like that. This is the reason for having the directives to stay indoors, because if you're indoors, you're not going to be subject to that. How this affects a person depends on what's released. So typically what we're worrying about is iodine-131 and cesium-137 are the two most common radionuclides in that situation. And there are a number of ways that these can be detected and watched for. For instance, someone who works in a setting like this, or if they're a nuclear plant worker, or if they're an emergency worker who's there for rescue or managing the acute damage to the building and trying to contain everything, probably would have a personal dosimeter. which is something you wear on your body that will tell you how much radiation and what types you've been exposed to. Yes, time? Oh, 2 minutes. Okay, I guess I have to move on here. You can also have Geiger counters are very useful for that, and whole body counting, for instance, can be done to determine a whole exposure. And then you can also look at various methods of determining an exposure, such as levels of white blood cells in the body. The best thing to do for this is simply removing the outer clothes and using soap and water to decontaminate the outside of the body. So this is not as severe a situation. The internal contamination is something that is of more concern in many ways. It's going to depend on, the effect of this will depend on how long-lived the radionuclide is. For instance, iodine-131 has a half-life of 8 days. So it's not something that stays around in the environment for 30 years, for instance, but if someone is present at a place where I-131 has been deposited and they ingest it, it goes straight to the thyroid gland. The thyroid basically takes in all the iodine it can from your diet. So this type of radiation can be deposited there and can cause damage to the thyroid. And the concern is, for instance, after Chernobyl, that even at relatively low doses of this, that it causes an increased risk of thyroid cancer, but it can also cause underactive thyroid hypothyroidism, and can also cause benign thyroid nodules. And this is the reason for instance, distributing stable iodine, potassium iodide, to prevent uptake of radioiodine. Particularly in children, this is very important because they're very sensitive to that. And in fact, they've seen approximately 6 times greater risk for thyroid cancer in young people, say under the age of 4, who were exposed to radioiodine after Chernobyl. Let's see. As far as preventing internal contamination, basically watch what you eat. So again, that's why the restrictions on milk from the affected areas, why the restrictions of green vegetables. In the US, we have something called RADNet, where the EPA is actually monitoring all over the country in many different areas. They monitor air, they monitor precipitation, rain or snow. They monitor milk and drinking water, and you can actually access all these online if you want to see what the levels are. And you can actually see very tiny amounts of radiation circulating around the globe from the Fukushima disaster, but they're very, very tiny. They can just be detected by instruments, and they're not medically significant. I guess this was actually covered in some of this. There are amounts of deposition of iodine-131 and cesium-137 in a number of prefectures in Japan. The levels are very low. The main thing is, as they say, they have evacuated the area immediately around the plant where there may be larger levels of deposition to prevent people from continuing to take in any of the radionuclides and potentially cause damage. So in summary, the severest effects of radiation on human health are seen if you actually are in the reactor room when something goes wrong, or if you're around an atomic bomb explosion, for example. Mostly what other people in general have to worry about would be external contamination, and then the internal contamination. There's some question about, well, could there be maybe an elevated risk of other types of cancers other than thyroid cancer? At Hiroshima and Nagasaki, there's a suggestion of that, but after the Chernobyl accident, there has been no evidence that there have been increased numbers of other cancers other than thyroid cancer. Thank you.
Thank you very much. Next, we got Mr. Pawlowski. I'm just going to collect the question cards. Thank you. You can still ask questions. I just want to go through those.
The pointer?
Pointer. Yeah, you got it. It's not very weak. It's not very strong.
I cannot see it very well here. Okay. Well, good afternoon. I was asked for giving a few remarks concerning the so-called passive safety systems. And I will talk about the existing reactors as well as the next generation reactors. First, the word passive, or passive safety system, or passive safety features. They can be divided, roughly speaking, into 2 categories. One, I would call it inherent safety features, which mean that certain things cannot happen. The other part is passive safety systems, which means that we buy time by employing systems which will be turned on automatically without any intervention by the operator, to buy time needed to turn on systems which will require external power and so on and so on. I would mention examples of both categories. Obviously, it will be examples because I'm not supposed to talk for too long. So let's say a classification of power nuclear reactors. Again, it may vary from source to source, but in principle, two are the current reactors, which started operating sometimes even in the 60s or early 70s. Then generation 3, which is the generation coming now. Generation 3 plus is very difficult to distinguish from generation 3. The only thing is that a bit newer, more advanced concepts. And generation 4, which is something very fuzzy. We talk about the future, and the future may mean 20 years or 50 years from now. It's really hard to say. Nevertheless, there is a category, generation 4 reactors. So I will start with a very simple example. It's a pressurized water reactor. A lot of reactors like this one operate all over the world. Actually, they constitute probably, I don't know, maybe 80–85% of all the power reactors in this country. Is around 70% as far as I remember. So this is the major factor in the nuclear technology market. What I would like to, I'm sorry, I did it too fast back. I needed a pointer. What I would like to point out is that the reactor itself is here. This is where all the nuclear fission reactions take place. But from a general engineering perspective, you can consider the reactor itself to be a heat source. It heats a high-pressure water. High pressure means something like 160 atmospheres or 2200 psi. And the water is circulated around what we call the primary system. The heat from the primary water is transferred to the secondary system water, where the pressure is lower, so water is converted to steam. Steam drives a turbine. The turbine drives a generator, and we have electricity. So this is what happens if a reactor operates normally. The issue is that again, here is a good example of an inherent safety feature. A nuclear reactor cannot be subject to a nuclear explosion. In other words, it is impossible physically to convert a reactor into an atomic bomb. So this is beyond any doubt, and because of that, we don't have any problems with the fact that the reactor power will increase from 3,000 megawatts to 50,000 megawatts. It's impossible. The problem, though, is that after the reactor shutdown, which happens immediately after anything goes wrong, the core contains still a lot of fission products. I think Dr. Harding mentioned it. And those fission products produce heat. A small amount. The order of magnitude is 1%. But out of 3,000 megawatts, 1% is 30 megawatts. And this heat has to be removed. Otherwise, if you produce heat, you do not remove it, the system will overheat. So we have a heat removal system here, this residual heat removal system. And normally, the reactor shutdown, for example, is associated with the action by, I'm sorry, again, I did something wrong. By this system. The question is, what happens if something goes wrong? If we cannot remove the system if the pump is down, for example. Then we have a problem. There are two barriers preventing radioactive materials from being released. One is the reactor vessel primary system. The other is the reactor containment. The issue is how to maintain the integrity of the reactor pressure vessel. There are two issues, pressure and temperature, overpressurization, overheating. Overpressurization is typically not an issue because we have all sorts of valves, safety valves. Such valves are installed on the top of the pressurizer, where the pressure goes up, the valve gets open and steam gets released into the containment. Overpressurization, we can typically delay this process and hopefully keep it in a safe position until other active safety systems can be recovered. The other issue is the reactor containment, because if we relieve steam from the primary system, the containment gets overpressurized. So this is one of the reasons the containment in pressurized water reactors is huge. But it's not the only way to prevent overpressurization. Another possibility, another system is the containment spray. In other words, we can spray cold water to condense any hot steam inside. Unfortunately, this is a sort of active system, but nevertheless, we have passive systems, such as the accumulators. These are huge vessels containing water at a pressure which is not the operating pressure, but something like, let's say, 50 atmospheres. And when the pressure inside the system goes down, this water automatically will be injected into the primary system. So there's a limited amount of water. Nevertheless, it will slow down the heating process inside the reactor core. And obviously, the major issue, as I said, is to maintain the integrity of the reactor pressure vessel. Another interesting feature of the system is the so-called reactor cavity, which is the space underneath the reactor core. You've heard the word China syndrome, that the reactor vessel gets overheated, the corium penetrates across the vessel, accumulates at the bottom, and then continues. If we have enough water, water gets collected inside the cavity, and it can even flood the reactor vessel, so it will be cooled from outside, thus preventing any significant heat up and damage. So this is for pressurized water reactors. Now the boiling water reactors, this is a slide which you've basically seen, is a Mark I containment. And here, oh my goodness, I've been doing something wrong. Here, the major difference is actually the primary containment is very small compared to the previous one. It consists of two parts, the dry well and the wet well. The fact that it is small is thanks to the fact that there is a system which forces steam to condense. So pressure buildup is prevented by using the so-called wet well. In this case, is a torus. So this is the original design. We have a Mark II containment design, which is more compact. The condensation process has been facilitated. You can see here, I cannot see. There's water inside the lower part, which is the wet well, and we have downcommers which basically force the steam to flow and condense inside a relatively deep pool of water, thus preventing really the overpressurization of the containment. Also, as you can see, there's one other difference. We have large pools of water, and this is refueling pool rather than spent fuel storage. In other words, we don't have spent fuel storage pools as in the Japanese power plant. And the water here, which really is quite, in terms of the volume, quite significant, can be used again to be injected into the system to prevent overheating. The next step is Mark III containment, which is similar, but it contains more water. And you can see here, this is the water stored during normal operation, and it has a different system which accelerates the condensation process, steam condensation in the case of any serious accident. The safety systems, including passive systems, are illustrated in this slide. Again, what you can see here is the so-called reactor core insulation cooling system or high-pressure emergency cooling system. The functions are similar. One is during normal operation, the other is during. What the system does is uses high-pressure steam still produced in the core, which, if the turbine is shut down, we don't produce electricity anymore, it can be sent to another turbine, and this turbine can drive a pump which will inject water into the reactor. So this is again a passive safety feature. Other things, prevention from reactor vessel overpressurization. Again, you can see safety relief valves, preventing the containment from overpressurizing, basically steam condensation in the dry well. And interestingly enough, all such systems practically worked in Japan, with some perturbations initially and time limitations. It turns out the biggest issue in the case of Japanese accident was that water was kept pumping into the system, but it was not removed. In other words, there was no way initially to remove water from the system in a safe manner so that it didn't end up in the ocean, but it could be cooled and returned to the system. So this was one of the biggest consequences of the accident, due to the fact that everything outside the plant was damaged by tsunami. Generation 3 reactors. Again, you can see quite a few types. 3 of them here are pressurized water reactors, 1, 2, and 3. And this is a boiling water reactor. To illustrate passive safety systems, I will use just one example. The AP1000, the Westinghouse reactor. You can see what it's going to look like. Sorry, again. In the future. 2 issues. Passive safety means having enough water and then using a simple physical phenomenon which is called natural convection. So here you can see the reactor containment, which has water stored on the top of it, and then has a flow path for air coming down and up. So cold air will come down, and then if the containment wall gets heated because of what happens inside, the air itself will be cooling the water and then flow out. So it will be clean water, and natural circulation means that cold water is heavy, hot water is light, so the circulation pattern will be provided by nature. And in addition, the water stored at the top can be used to cool the containment wall as an additional mean of cooling. Water inside the system, you can see a lot of water, and this is a huge pool which can be used to inject water. And again, the pool is located above the system, so gravity will drive the flow. Another issue is providing extra volumes. We call them control makeup tanks. Those tanks have water which is normal at maybe not room temperature, but higher than room temperature. It is pressurized, but normally it's neutral. When the system needs it, the circulation starts through those additional volumes of water, so we have an extra amount of water which provides more coolant and allows, even in the case of leakage, for continuing cooling the reactor over a longer period of time. Generation 3 plus. I have one example again. A reactor originated too fast. In this country, it's a General Electric project, a reactor which is different from everything else because it does not involve any pumps inside. Safety features are clearly seen here. Water, 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 and natural convection. You can see a lot of pools of water everywhere, and you can see the fact that hot fluid will have a tendency to flow up, and then after being cooled, it will flow down. So it will be a natural circulation loop provided thanks to the presence of water and a heat exchanger. There will be no active elements here. Also, the volumes at the bottom, the lower part, serve as heat sinks because any steam accumulated inside the primary containment will be condensing inside those large volumes of water. Generation 4, just 2 words. We have a lot of reactors. I would like to focus on one. This is very high temperature reactor, sodium fast reactor, supercritical water reactor, and another possibility combination of sodium reactor using supercritical CO2. But I would like to focus on one reactor, which is the so-called molten salt-cooled reactor with circulating fuel. So the fuel is also the reactor coolant. In this case, this is a concept which is not known. Now it received a lot of attention, and the features here are, thanks to the kind of liquid used, which is, again, molten salt, the pressure is very low, no possibility for evaporation, no accumulation of fission products because they can be removed during the operation, and those fission products which produce heat will not accumulate inside the reactor, so it will be possible and easy enough to cool the core and the fuel in general by using natural convection. The last slide is here. What I would like to mention is that current generation designs already have a lot of passive safety systems. In the next generation reactors, the role of such systems will become even more important, and the accident in Japan was a very serious and very unfortunate event, but it will stimulate efforts to improve designs of future reactors. Thank you.
Thank you very much. Okay, so we have a few questions here, and I distributed 2 of them already. So if you have more, please keep sending them here. So I think the first question is for Professor Manzari. So I'm going to let you read it and answer it.
So the question is, what are effective ways to mitigate tsunami damages? Example given, like offshore structure to dissipate waves. I am not aware of effective ways to dissipate, the waves of tsunami. All I know is that the current trend is to be able to sense it earlier, and you basically improve the warning system that they have, because the earthquake wave through the ground reaches the land, the shore much earlier than the actual wave. So they had about an hour to know that the tsunami probably is going to reach the Fukushima plant, but still they couldn't do anything about it. I mean, probably the earthquake already shut off the system and all those, but really the fact that this is going to a wave with a height of 14 meters is going to submerge this plant is very difficult to dissipate it right there in the ocean. So I'm not aware of it. I think this question is from Professor Ken Chang. If you have any comments, I would welcome that. Yes.
So very briefly, because we have a lot of questions to go through.
I've seen some of the offshore structures. They have certain kind of breakwater type of thing to absorb the energy. Something like this along the shoreline may be able to dissipate some energy.
Thank you. I think we have another question for Margaret Harding.
Yes. The question was, where did the hardened vent from the containment exhaust to, and is it the same in the U.S. plants? In the United States, there was a requirement after 3 Mile Island and some concerns about hydrogen explosions here for there to be a containment vent, and it wasn't in my drawings, and I apologize for that. It actually it vents out of the building completely, and what a hardened vent means, for those that don't understand, is that the vent is structurally strong enough to withstand the idea that the hydrogen in the vent explodes, but the vent itself doesn't come apart. It's not clear in Japan exactly what was done there, and Mr. Yamachiko might know that. I've done some research on it, but whether or not the vents in the Japanese plants were hardened and where they were venting to. This is one of those things where the vent is still going on. They're still working to stabilize the reactors, so we haven't been able to research and study and learn all of those things. That's one of the questions that will be answered before we finish understanding this event.
Yeah, as far as I know, and as for the Mark 1, all of the Mark 1 has the hardened.
Does have a hardened vent. Okay, yeah.
Reflecting on the TMI.
Good. Okay. Thank you.
So actually, there was a follow-up question on this for either. Oh, please.
Yeah, a quick comment. Based on what I've seen the records from Japan, the radioactivity release was mainly in spikes, very sharp releases, and then stop. It clearly indicated it was a part of venting.
Yes.
Exactly how and where it is unclear, but it really indicates that it was a system which was opening a valve and closing it. So it wasn't due to a failure, but due to the fact that the overpressurization could only be prevented by releasing radioactive materials into the atmosphere.
So there are actually a couple of follow-up questions on this. Why did the hydrogen accumulated in the building when it should have been vented to the outside? Is there any suggestion on this?
Can you say it again?
Why did the hydrogen accumulated in the building versus of being vented to the outside?
Well, the hydrogen, the major hydrogen release had to do, as far as I understand, with the spent fuel storage pools, which the explosion.
In Unit 4, that might be the case, but
The
in
fact that
Units
the
1 and
buildings
3,
exploded,
in Units 1 and 3, it's not as clear because the explosion occurred before the water levels in the pools were too low. So not as clear where that hydrogen came from.
Again, our exchange illustrates a lot of unanswered questions.
Yeah,
really a lot
exactly
of work
right.
will have to be done. But what I wanted to say is that the building, the structure which exploded, is a very light structure.
Right.
So it's not a safety feature. It's basically the structural element, and it could explode only because of something that happened very close to it outside the primary containment. And the way I read it is that it was hydrogen production outside the primary containment, and the only source was the spent fuel pools. But again, we have to wait for
Research.
a more thorough analysis.
Mr. Yamashika, do you have any?
And so I showed that diagram from the Unit 1 to Unit 4. So maybe this helped and understand. But also I heard so many comments or the speculations.
Yes.
But I can't prejudge at this moment. But I have to let you know that I think that a special investigation committee will be organized by the government in the near future, which is responsible for what and investigate what happened, what the cause is that.
Thank you very much. Another question is, in some report, it says that the diesel generators were swept away by the tsunami. Where were the diesel generators installed? And the fuel tanks?
All of the generator is installed and annexed to the main building. Yeah.
So were they facing the sea, or were they behind the building? That's kind of the question.
Unfortunately, and I don't have information in detail. So, but so the every diesel is as I showed in my presentation paper on page 13. So.
Would it be possible to switch to the third presentation, please?
Yes.
I think there's.
Yeah, it was.
No, we need the third one, number 3.
This one, yes. But you have to direct it over there.
Okay, well, we can come back on.
Yeah,
we'll come back on that question after then. I have a question here. How is sea life affected by radiation?
Again, it would be similar to effects on any other living creature. Different types of animals have different amounts that they're affected by radiation. They may be more resistant to radiation or less resistant. Basically, with the release of contaminated water into the ocean, there are two things that are going to take effect. One is that releasing it into a large volume of water will shield the creatures in the ocean from transmitted radiation. The main concern is going to be if they ingest any of it. And again, it becomes extremely diluted, so the dose acquired by any particular sea creature will be very small. As I understand, there is a lot of testing being done in the area, and I believe there's only one type of fish that's been shown to really be accumulating measurable amounts of radiation. And they are fish, I think they're bottom dwelling, that live very close to the areas where the water has been released. Again, it would depend on the target organs that the radionuclides are attracted to, and the total dose. And again, the half-life of many of the radionuclides, such as iodine-131, is very short. So it would not be something that would be dangerous to humans, but it could conceivably cause, health problems for sufficiently exposed fish, I suppose.
Thank you. A question on the design of the plant itself and the scenario. Could we have avoided this design, this incident, and what are the lessons learned from this?
There's a couple. Well, first of all, the plant survived this huge earthquake quite well. They went through the earthquake and shut down exactly as planned, and the diesel generators all kicked on. I don't think that there was a real thorough time for a real thorough evaluation of any structural issues before the tsunami hit. Clearly, a 14 meter tsunami hitting a plant that was designed for, I believe, a little over to 7, somewhere around 7 meters. Obviously, if they'd known that the larger tsunami was potential and had higher walls or hardened structures around the diesel generators or a couple of other things to prevent the diesel generators from being flooded or washed away, the plant, we would not be having this conversation because they would have worked as planned and it wouldn't have made the news. So yes, there are design things that can be done. There's some in the United States as well. There are a number of activities going on to look at what we understand to have happened there, and is there things we can do to backfit these same reactor designs in this country if it's needed, or if it perhaps has already been done as a part of some of the other efforts going on with reactor safety in this country. So the answer is yes.
If I may add just a quick comment, that the earthquake was strong, but the reactor systems survived it very well.
Oh, yeah.
The damage was due to tsunami mainly, rather than the earthquake itself. The conventional part was really severely damaged, and even after the generators were brought back or the power was installed, there was still some time needed to start injecting water because the water lines, the pipelines were damaged, pumps were damaged. So everything what was on site was damaged because of the tsunami.
Yeah.
So the lesson learned, well, again, is that you have to anticipate what the nature can do to us in a more conservative manner, but 8.5.
Yeah.
It
They
was
were designed for
stronger than anybody expected, and the tsunami itself was incredibly.
Right. And one of the issues to remember is that the country suffered huge infrastructure issues with the earthquake and tsunami on the country of Japan, which really affected some of the ability to respond to what was happening at Fukushima. People missing and dead is not to be ignored, and you've all seen the pictures of the devastation in the area, and so that, I think, made it that much more difficult for the country when they did realize they had the diesel generator flooding. They couldn't simply turn around, grab a bunch of people, and get in there and do something because they were stretched so thin with the emergency responses across that entire coastline.
So since we're talking of tsunami, I have a question here on PRA, probability risk assessment. Were probability risk assessment performed for tsunamis?
Yeah, I have no idea how much, to what extent that PSR was considered for the tsunami. But basically, normally we assume the size of the earthquake, and then we will estimate the size of the tsunami. Yeah, of course these days, I know that there is some study for the PSA is utilized for some severe accident analysis. But unfortunately, I'm not sure to what extent the PSA is incorporated in the for the tsunami evaluation. Yeah.
Thank you. Another question is how many nuclear plant workers were exceeded the safety limit and radiation level? How many received more than the maximum level they can receive?
As far as we know right now, 2 women have more dose than is allowed in Japan for female workers to date by quarter. There's a quarterly limitation. But my understanding is that no workers have exceeded the 250 millisievert limit.
No, and the government raised up the maximum level from the 100 to 250. But
yeah.
Most of the people, workers are monitored, so that those rates for the workers don't
Right.
exceed.
Right, they just released that.
Yeah, so I'm not sure that how many people had those more than 100, but if
23.
If there is, and a very small number.
Yes.
So actually, that's an interesting point. Maybe some of you can address this. Why in different countries the level of radiation limits are different?
I can tell you what they are in this country. Normal radiation limits for workers in this country is 50 millisieverts a year. 5 millisieverts, 5 sieverts. I'm going to get this wrong because I think of it in REMS. 5 REMS. And in emergencies, it's 25 REMS. And I never convert it correctly. Yeah, okay, thank you. I feel better that she can't do it either. And in Japan, I believe 5 REMS is also the standard limit for normal circumstances, and in their normal emergency is 10 REMS or whatever that is in sieverts, and they upped it to the 250, which is the equivalent to 25 REMS. Why it's different in each country is because each country has its own way of writing the laws.
Well, I think one reason is that this is a very difficult issue, that there's not enough evidence, fortunately, because it would mean something rather
linear, no threshold.
unpleasant.
Right, exactly.
Experimenting with radiation and then humans is impossible, and because of that, a lot of limits are more or less arbitrary on the conservative side.
Yes.
Right.
And who is more conservative, who's less? That's an open question.
And part of the discussion as well has been no one really understands low-level radiation effects very well because most of the data that we have has historically been from Hiroshima and Nagasaki, which were for very large whole-body exposures. So there's a tremendous discussion continuing to go on about, well, with very low levels of radiation, such as from medical scans, I know what really are the effects of that. And so they were saying, for instance, is it a linear no-threshold dose? So as you go from very small doses to very large doses, there's a linear increase in the effects? Or is there a threshold where below a certain amount of radiation exposure there's essentially no effect and then it suddenly increases? And no one really knows which model is correct at this point, and that's partly what we're trying to figure out. And that explains some of the inconstancy in the limits that are set.
So since we're talking of radiation as well, there was a couple of questions on how will the environment be cleaned of contamination.
Well, one of the easiest ways is time. Iodine-131 has a half-life of 8 days. So in 80 days, it is 1/2 times to the 10th power So it's undetectable at that point. You really can't see it anymore. So that's one way that you deal with it, and iodine is one of the major contaminants. The other contaminant that's more problematic would be cesium.
Which has a longer half-life. It's about 30 years. But I guess that's going to be the problem, is what the long-term consequences of that. Basically, you want to try to prevent it from getting into the food chain. And that, for instance, at Chernobyl, there's still the zone of exclusion where people have to live because of contamination with longer-lived radioisotopes like that.
But the good news is it can be washed off, or you can take off a layer of topsoil. It rests on the topsoil. So we know that some of the schools in the area of Fukushima are remediating by taking a certain level of the topsoil off, so that they take off any cesium that was in that topsoil, and then that can be either taken to a low-level waste repository, or perhaps some of it cleaned off. The cesium, you can grab cesium. There's different ways of basically chelating the cesium out of it. I got the right term. How scary. I'm not a doctor. I never took biology, so when I get into this, I get a little lost. But at any rate, you can actually clean the topsoil off, and I know that's one of the techniques that's being used at some of the schools.
Okay. Let's go back to the plant, to the sequence of events at the plant. One of the questions was why, and I'm going to add if. What caused the leaking of the spent fuel, if they leaked?
Why?
Yeah. Or did they leak?
Did it leak?
The spent fuel pool, did they leak? And if they leak, why?
The leak?
Yeah.
Did the spent fuel pools leak?
Well,
We don't know.
We don't know. We don't know. All we know is that spent fuel generates heat, and in one of the reactors, there was a relatively large amount of spent fuel stored because of the refueling, which happened a month or even less before.
5 months, actually. They'd been shut down almost 5 months at that point.
And spent fuel generates heat. And those are back-of-the-envelope calculations. You can clearly see that even the amount of, let's say, 0.5% of the total power, if you have it stored in spent fuel, the water, let's say 10 by 10 by 10 meters, which is 1,000 metric tons, will start heating within, if not hours, then days, and eventually will start evaporating if you do not provide any fresh water. So the fact that the spent fuel got uncovered and overheated is because of the heat balance. Whether there was a leak or not, I really don't know. I don't think we have solid evidence.
The pools are actually were designed to withstand these large earthquakes, and there's a number of analysis that have been done in this country for this kind of an event here, and very few ways for them to actually leak. Remember, we're talking about a very thick, no holes tub, and there's not much in it that could punch a hole in it, and it's steel, so it's not prone to cracking per se unless you do the kind of a credit card thing. So there's actually not clear that they are leaking as much as they are evaporating. The other thing that could have happened that's been discussed is, remember that there was a 9/0 earthquake. If you've ever witnessed a swimming pool in an earthquake, large amounts of water jump out. So it's possible that there was some slosh in the earthquake that would have cost even more water to have come out of these pools. Combine that with evaporation, you start to lose a lot of water.
And the fact that the situation was really difficult to judge it can be illustrated using a very simple example. Some time ago, there was an official statement, I'm not going to talk about details, saying that one of the pools was completely dry. And then, a few hours later, there was a picture taken from a helicopter showing that the pool was full of water. So it's very difficult to say what happened, whether the water was provided by those fire hoses or it wasn't really fully uncovered. And I suppose the truth was somewhere in between.
Probably.
Okay, thank you. A couple of questions on the plant design. Apparently, some studies were done saying that a wave as high as 15 meters could happen at that plant. Why was the plant not designed for that kind of tsunami?
in the original FSAR, they did not anticipate a tsunami that high. I've looked at the documents from 1971, and they anticipated a tsunami about half the height that they actually designed the plant for. The higher tsunami is, I think, later data, later information, and I'm going to leave that to others to respond. I can tell you, though, that the original design, they did not anticipate a tsunami that large.
Yeah. The original and design for tsunami is around 6 meters.
Meters,
6
yeah.
meters. So the design was considered and taking into account and this kind of
Right.
evaluation. Right.
Couple of and on the plan design itself, they said that that's Professor Manzari. They said the resonance frequency of the building was 4 hertz, and the earthquake hit at 4 hertz. So one person would like to clarify this, and is this a good or bad design?
Basically, what I was trying to say is that the fact that these two are so close, the structure really got a lot of energy and was able to sustain this earthquake very well. This was the idea. The idea was not that this is good for the structure, is that even though it's so close to the fundamental frequency of the structure, you still perform very well. Remember, this structure was designed only to sustain a maximum acceleration of 0.49 g, and it got something around 2 point some g. So this is one thing. The duration of the motion is also very, very long compared to what you normally design these buildings for. So the engineering, in fact, of these buildings are fantastic. You know, if someone look back at 1967, the knowledge of earthquake engineering 1967, and look at what we have today, is just you cannot imagine how much progress has been made, and the type of analysis those days they were able to do are so elementary that even today, if we were to design or analyze a building that is 10-story building, we use much more sophisticated tools than they did for analysis of this particular structure. Yet the design was so good that was able to do this. The tsunami wave generated a 14 meters of water height, and design was for 5.7. The acceleration that was designed was less than 0.5. It took something around 2 g. So it's amazing.
Thank you. On the plant itself, so Fukushima Daiichi was more north and potentially closer from the epicenter. Why was it less affected than Fukushima 2? Or Fukushima 1, sorry.
The Fukushima Daiichi fortunately had assured the off-site power. So the utilities and makes the best effort to keep the electricity from the outside. Yeah.
But also, I think tsunami itself is not just the epicenter, but also the waves, which were much stronger at the Daiichi plant than the other one.
Yeah, isn't that the offshore geography that would affect how high the wave is at one plant versus the other?
Yes.
Right.
So we have time for let's say two more questions. One of the question which let's go back to Professor Bittner here on the effect of radiology. You didn't two things. So you didn't mention strontium-90, and another issue is cesium has a very long half-life. Cesium-137, about 30 years, but you recirculate it in your body much faster, about 70 days. How does that affect the effect of?
Okay. As far as strontium-90 goes, that was actually not a major radioisotope released at Fukushima. The issue with strontium-90 is that chemically it acts very similar to calcium, so it can be deposited in bones, and in that case would have a very stable place in the body and would be there until the physical half-life is undertaken, so it does not circulate in and out of the body. So that's why strontium-90 is an issue. If it does accumulate, it can cause such things as malignant bone tumors and things like that. But that was not a radioisotope that was released in this case. As far as cesium-137, that's correct. The physiologic half-life is much shorter than the chemical half-life, the physical half-life, rather, I should say, of cesium-137. You know, the effects of it have not been as well studied and established as iodine-131. One advantage, even though it has a much longer half-life and persists in the environment much longer, is because the half-life is long, for each atom that's ingested into the body and taken in, then the rate of decay is so slow that the actual radiation dose per atom is quite small, and so the immediate effects are much less than, say, I-131 with a shorter half-life. You know, that's partly what's being studied. I know there have been some studies about Chernobyl looking at effects of cesium dose on occurrence, for instance, of thyroid cancers, and they haven't, which has been the major malignancy found after that, and there hasn't been a strong association with that. So the end effects are somewhat unclear. But again, it's because it's a longer-lived isotope, the rate of, unless you have a massive dose, the amount of radiation delivered to the organism will be relatively small over time.
Okay, two very brief questions, and we're going to end here. Why was there no natural circulation passive safety system in the GE design in Japan?
Actually, Dr. Podowski talked about that. There is a natural circulation system, and it actually worked part of the time. There's a battery that holds the valve open, though, and the battery gave out. But that system is effectively natural circulation. It's using a steam-driven, it's using the steam of the reactor to drive a pump, to push water in. It's also dumping the steam into the torus that we talked about. The problem is that, as Dr. Podowski described, the water isn't leaving, so the heat isn't leaving the total system. It is staying inside that containment and building up. And two things essentially didn't work over time. It was assumed that you would get offsite power, either the diesel generators or offsite power, back on within 8 hours or so. So that's the limit of the battery life. And then the second one was the heat wasn't leaving the system. Once the water in that suppression pool exceeded 100 degrees centigrade, it's no longer doing its job in terms of helping to cool and cycle, because now it's to boiling and the containment is effectively at atmospheric pressure. Part of the reason that they didn't put in these big passive safety systems that the ESPWR has is technology to some degree. GE had attempted to design passive natural circulation systems in some of their very, very early reactors, pre-BWR1s. And it turns out to have some stability issues that they were not able to solve until they got smarter and developed some additional techniques that are used in the ESPWR. So there was a limited ability to use a fully passive emergency response system. And I think there was also some view that we would never go 3 days without the diesel generators being available. And again, that's kind of one of those, the hubris of humanity, that we think we can do those things. So they're learning from that and going to these more passive systems. And the goal in those passive systems is that they can run for 3 days. You can literally walk away from the reactor and it will continue to remain cool 3 days without human intervention. The idea being that at the end of 3 days, if you haven't been able to get power back, there are other bigger problems.
Well, I would add one thing, that based on my observations, the accident will change the perception of passive safety. Typically, so far, even for the next generation reactors, the idea was we have to provide enough water to cool the system. Now, the apparent problem was not with the water which was put into the system, but the inability to remove the water from the system. For one, it was radioactive. No means provided because of the damage to remove heat from the hot water. And this was the biggest problem. So there was enough water inside the system. Torus at one point remove it. So I think it will be an issue really be revisited and reactor safety.
So since we're talking of to end here, we're already at. Will we have Gen 4 reactors online, and why does it take so long to develop them?
Well,
Not gonna
it
touch
depends on who presents the plans. I've followed Department of Energy. When I talked to a representative house, he was even more pessimistic. He said, well, next 40 years we'll have to struggle with the current generation of light water reactors to make them anything beyond that.